Hello everyone, welcome. My name is Afonso Fonseca. I am a PhD candidate in the graduate program in computer science at the Informatics Institute of the Federal University of Goiás, Brazil. I will introduce you to the paper Automatic Tuberculosis Detection Using Binary Pattern of Phase Congruency, the result of work carried out together with colleagues Juliana, Gabriel, and Deborah, under the guidance of Dr. Fabrizzio Soares. So, for this presentation we prepared the following outline, a brief introduction to the main subjects under this study, our purpose, the proposed method to achieve it, the results achieved so far, and finally our conclusions. Introduction. Tuberculosis, or simply TB, is a serious infection caused by the bacterium Mycobacterium tuberculosis or Koch bacillus that affects mainly the lungs, but it may spread to other organs. The main symptoms are fever, fatigue, weight loss, persistent cough, blood in cough and night sweats. Although tuberculosis, TB, is preventable, treatable, and curable, it still represents a serious public health problem worldwide, mainly affecting the most vulnerable populations. The high costs of the entire health chain prevent these populations to seek a diagnosis, implying directly not only to the lack of treatment but also the underreporting of the disease. The World Health Organization, WHO, shows that, only in 2020, 10 million people were infected worldwide and 1.5 million died by TB, in a daily average of 4,100 deaths. Therefore, affordable and scalable solutions, low cost, of rapid response, and easy implementation are essential in fighting tuberculosis to aid in correctly screening, triaging, and diagnosing patients. Thus, chest X-rays, CXR, for all their characteristics, such as low cost, high accessibility, and rapid response, are an essential tool for diagnosing and following TB cases. Meanwhile, advances in artificial intelligence show that AI can also be a strong ally. Two TB-related conditions exist, latent TB infection and TB disease or active TB. In latent TB the bacteria can live in the body without making you sick, so people with latent TB infection have no symptoms, they don't feel sick, and they can't spread it to others. They usually have a positive skin test reaction or positive blood test. More importantly, they may develop TB disease if they do not receive treatment for the infection. In these cases, the TB bacteria remain inactive for a lifetime without causing the disease. However, in some other people, especially those that have a weak immune system, the bacteria become active, multiply, and causes the TB disease. On the other hand, one can have an active TB if their immune system fails to stop the tuberculosis bacteria from growing. People with active tuberculosis are sick and they can spread the bacteria to people around them. Still, on CXR scans, TB may show up as consolidation, cavitary lesion, pleural effusion, hilar lymph node enlargement or mediastinal, among others. In this study, a public dataset named TBX11K established by Liu et al. 2020 is used. The dataset has 11,200 CXR images, however, in performing this work, only 8,976 had an associate label available and were used. The table shows a summary of the dataset, where we highlight the two main classes that we'll use, and whose sample number contains an evident imbalance. Purpose. In this study, we propose a low-cost and high-efficiency computational solution specially developed for regions, environments, and equipment with few resources that assist in diagnosing tuberculosis cases. Proposed method. To achieve the objective of our proposal, we build a neural network model powered by features of binary pattern of phase congruency. Binary pattern of phase congruency, BPPC, is an adaptation to the local binary patterns, or LBP, where the intensity value needed to calculate the traditional LBP is replaced by the phase congruence, PC, value in the corresponding pixel. PC models are, in turn, essential pattern descriptors, as they provide a measure independent of the overall signal magnitude, making it invariant to image illumination and contrast variations. Thus, as the PC image describes different feature categories, the LBP code is also designed to describe different categories. The first step in BPPC is finding the image's PC in different orientations. Then, taking 4 directions and dividing the frequency plane uniformly, the resulting input image features are obtained by concatenating each of the 4 BPPC images histogram in one direction. For each, the same number adopted in Turin ETAL 2018 of 177 bins was used so that the final vector has 708 features. The BPPC feature extraction process is shown in this figure with an input CXR image, its 4 PC images, followed by the corresponding BPPC images and, finally, the BPPC histogram representing the extracted features that will be used with the input of our N model. Our model is a feed-forward neural network with N input nodes, one hidden layer with 3 neurons, and the output layer to the binary classification scheme, outputting TB or non-TB cases. We chose this network because they are the first and simplest categories of artificial neural networks developed. It has excellent predictive capability, independent of the probability distribution information from the data. It is high efficient due to the parallel structure and the ability to improve performance through experience, and it has been successfully applied in a wide range of medical applications. Thus, to evaluate our model, we applied a 10-folds cross-validation scheme and we calculated the following measures: accuracy, sensitivity or true positive rate, specificity or true negative rate, area under receiver operating characteristic curve. We also draw the model's ROC curves in its corresponding Sankey diagram. And finally, the DOR value is also calculated to measure the effectiveness of the diagnostic test proposed by the model. The experiments were conducted on a desktop equipped with an Intel Core i5, 2 GB of RAM, and it ran on MATLAB R2014 and a 64-bit Windows 10. The deep learning and signal processing toolboxes were used. The equipment did not have GPU-accelerated graphics processing. Results. This table shows the results for each fold in the cross-validation process. And, in the last line, we show the mean results and its standard deviation. Note that the ACC and TNR have smaller STD than TPR, which is partially explained by the imbalance of classes, since there is a much smaller number of samples of TB cases. In general, the model is stable and obtains expressive values for all measures. Here, the ROC curves confirm the effectiveness of the model while giving an AUC value of 0.99 with an optimal operation point close to 1. About the Sankey diagram, it presents a new way of looking at the model's performance through the flows of its instances from input to output. In this diagram, the flows between input and output instances with crossed classes represent the misclassifications of the model, such as Fn and Fp of the confusion matrix, while the direct flows between classes are the hits. The more insignificant or non-existence fractions of cross flows, incorrect, and the greater the fractions of direct flows, correct, the better the model. Thus, the thin crossed lines shown in the diagram represent a model with low errors and high accuracy. Now, in this table, we bring a comparison with some related works. Although some of them used other datasets, they are useful because they show the different methodologies that have been used to address this issue. From this comparison, we can see that our proposal presents competitive results compared to other studies, even those that used the same database. Moreover, our proposal used only 708 input features, very different from the millions of parameters used in DL models like CNNs. It has one single hidden layer with only 3 neurons, maintaining fewer degrees of freedom and being less prone to overfitting. Our BPPC feature extraction process takes rightward arrow 0.57 seconds per CXR image. For building and training, it only takes rightward arrow 200 kilobytes, while the average processing time for each image is about rightward arrow 150 milliseconds. And it takes rightward arrow 7 milliseconds to infer a new image. In addition, the model obtains a DOR value of 4755.55. Conclusions. Thus, considering our initial proposal for a low-cost, high-efficiency computational solution developed especially for regions, environments, and equipment with few resources, which help diagnose tuberculosis cases, we build a single-layer neural network. That is an intelligent, speedy, low-cost, and high-efficient solution to diagnose TB cases. The system was evaluated in an extensive public TB database, named TBX11K. It has high sensitivity of 97.52% and AUC value of 0.99. And it shows a remarkable DOR value above 4,500. Finally, we showed a feed-forward neural network model using binary patterns of phase congruency features. This build model used few computational resources, memory, time, and power, obtaining competitive results. Thus, we can conclude that the BPPC resources are valuable and effective in discriminating TB cases in XR images, representing a valid alternative in the construction of artificial intelligence solutions for the diagnosis of TB. Thank you for your attention, and any questions, please send an email to Afonso@inf.ufg.br.